Okay, today is 7.3, and this is basically where we teach you one more thing about rationals, uh, and then we get into word problems, okay? So the rational thing we haven't taught you yet is how to solve rational equations and inequalities. I'm going to get to that, but here's a review of the old stuff. This is what we did before, and on this one, it's really easy to find the vertical asymptote. The thing on the bottom tells you the vertical asymptote. What if there'd been another one just like it on top? Then it wouldn't have been an asymptote. It would have been a hole. All right, but there wasn't one on top, so it's a vertical asymptote at x equals -2. So I go over here to -2. I missed that kind of, but my alignment's off, so be good. So then, oh, that's +2. Okay, I really missed it then. I'm going to try again. Actually, my alignment's better than it was before. Okay, so there we go. There's an asymptote. What about the horizontal asymptotes? Who can tell you about them? Bob. Is this a bob, or is it a bot, or is it a sob? This one's a bob. It's bigger on the bottom because it has a power of 1 on the bottom, and there's no x at all on the top, which means it's kind of like there's an x to the 0 on the top. But either way, the degree of the bottom is 1, which is bigger than the degree of the top, which is 0. So it's a bob. What's the rule for bobs? It's y equals whatever's outside. In this case, there's nothing outside, so we could say y equals 0. That means there's an asymptote right there. Any questions so far? Okay, then what if they're the same? What if they're the same on both? So if it would have been like x over x plus 2, that'd be the same on both. Yep, it'd be the ratio of the lead coefficients, 1 over 1. And how about in the weird case where it's bigger on the top? No bots. If it's bigger on top, there is no, it's a no bot. Bigger on top, no horizontal asymptotes. Okay, now we can talk about slant asymptotes later, but there's no horizontal asymptotes. All right, and the slant, just let's talk about slant asymptotes for a second. If it's bigger on the bottom and it's got something out here, then there's a slant asymptote, and that's the kind that we would expect you to be able to do. So let's say it was 4 over x plus 2 plus 3x. Well, then you'd have a slant asymptote at y equals 3x. All right, instead of if it had been just something simple like 1 over x plus 7, you get how the whole function would have to move up 7. That moves the horizontal asymptote up 7, so it's y equals 7. So it's whatever's on the outside of the fraction, even if it's just a number, it's y equals that. All right, so that's a quick review. And then holes, there's neither one of these two have holes because there's nothing on the top here to cancel things on the bottom. Even if the bottom factors beautifully, there's nothing on top to cancel it, so there's no holes in either one of these two. But holes are one of the #1 things kids forget because they get done graphing this really complicated thing, and they finally get done and they forget that there was supposed to be a hole right there or whatever. So be careful to always remember to graph the holes. Okay, the last step on these is to actually get some points. Like I've got my asymptotes, where is the actual graph? Is it here and here? And don't just say, well, it's always here and here. No, it's not. It really depends on the problem. Yes, it's often in those two spots, but you've got to try some points. Like for instance, XY chart. What is the best point to choose? Well, that's kind of a judgment call, but you want something that's smaller than the vertical asymptote. The vertical asymptote's at -2, so maybe -3. Get why I'm doing that? Because I need something to tell me if it's either up here or it's down here. So I picked x was -3 here to like tell, am I going to go above 0 or below 0? When I put in -3, I get 4 over -1, which is -4. And -3 gives me -4, and that tells me it's down here. So, -3, actually I can erase this now. And put the asymptote line back in there, slide it over a little bit, and then -3, -4, there's a dot right there. Alignment's off again, thanks for being patient. Okay, so then I know how asymptotes work, so I know that this must get really close in both directions. Shouldn't be touching it like that, but okay. And then I'm going to try something bigger than -2, like maybe 0. Put in a 0 on my little chart, and I get 4 over 2, which is 2. So 0, comma 2, being over 0, up 2. There's a dot there, so I know it must be up in there. There we go. Good enough. It's just a sketch. Okay, that's the process for graphing and then finding vertical and horizontal asymptotes and holes. From here, you can see the domain pretty easy too. The domain is going both directions. Does it go forever in both directions? Yes, with the exception of one thing. What is it never, as it goes from left to right, what is the function never able to be? -2. So you could go like this. Everything except -2. So there it is in graphic form. If you wanted to say in intervals, -infinity to -2, and then -2 to infinity. Okay, so that's all the stuff you're supposed to know so far. A lot of factoring going on. Would you please go to number 13? I know I didn't assign it. I, in the video, told you not to do 13, but I want you to do it right now. So if you want to find it in your old assignment, and do number 13. The top and the bottom factor nicely. There will be a hole, but the actual picture is harder because there's an asymptote missing, so it's harder to tell where to graph it. You're going to want to use an XY chart and get several points. Make several points on the XY chart, and you'll start seeing there's actually 2 parabolas involved, or kind of close to parabolas. I'll pause for a second while you give number 13 a try. Okay, you should have factored the top and got an x out, and then an x plus 1 and an x plus 1. And on the bottom, you should have an x plus 1 and an x minus 2. Then, when this cancels, it creates a what? A hole. Look at your graph. How many of you have the hole shown on your graph? All right, that's a really common thing for people to forget. How do you get the hole? Well, you go y equals, this is the leftover function now, x plus 1 all over x minus 2. Notice I don't leave the other one in there. This canceled out. It's gone now. But when I stick -1 in, technically it would crush this. It would turn the whole thing to mush because the bottom turns into 0 and it shouldn't have any answer. But we need to know exactly where the hole should be located. I know it's at -1, but is it there? Or is it here, or here, or here, or here? And the way you can tell is by sticking -1 into the resulting function. -1 goes in here, here, and here. And you get a 0 on the top. That makes the whole thing equal 0. And therefore, -1 comma 0 is where the hole should be. That means there's an empty spot right there. There was also an asymptote from here. That x equals 2 is an asymptote. That means there's a line running right there. And then for the rest of your graph, I'm going to put in a few other points. Let's say I make my XY chart and put in 0 and I see what happens. I get 0 times 1 makes 0 on the top. All I need to hear, 0 on the top, as long as it's not 0 on the bottom, which it isn't, gives me 0. That means there's a dot right there, because 0 gave me 0. Now I'm going to try to put in 1. When I put in 1, I get 1 times 2 is 2 over 1 minus 2 is -1, which makes -2. 1 gives me -2. It's going down again. And now I know, oh, it's a parabola. Here's my graph. It goes like that. That's just by graphing a few points, I get the idea that it was going back down again because these were at the same level as each other. All right, then if I stick in another one, I know it's to be 12. It's off the graph, but there's something up here, and you'll find that it, again, starts going up again. So you have a parabola on the left side and that's upside down, and you have a right side up parabola on the right-hand side. And technically, there's a slant asymptote in here, but I am not going to try to explain that to you. Say that again. Okay, and I could believe that that would be at x plus 3. That would make sense. Can you explain that to me?
You take the numerator and then you divide it by the denominator.
Okay, well, here's my numerator.
Of the original
Oh, in my original equation, I take the numerator divided by the denominator. So help me understand how I would divide these two. I get these canceled, but now I got this and this over this. How does that end up being? Oh, you use long division. Okay, this is beyond what you guys have to know, but so then I would go x plus 2 goes into x squared plus x. Do long division, and it would tell me the 3x.
I used the original.
Okay, all right, so you use the original, and you did long division off of that. It should still work the other way, but maybe it won't. And then you did long division on these two? And what did it come out to? All right. All right. So when he got this long divided out, it came out to x plus 3, which does make sense that there would be an that the asymptote that I described as being about here. I'm off a little bit. It should be a little bit higher than that, and that would be the y equals x plus 3. We would not need you to be able to do that, okay? The slant asymptotes I would need you to be able to see are really obvious ones like this. Do you get that outside my fraction I have this, and this is a bob, which is bigger on the bottom, and therefore it's y equals 3x would be a slant asymptote on this one. All right, so that was meant to be mostly a review of how you do the old stuff. Let me talk about the new stuff for a minute. I'm going to take a moment to ask you to do something very unusual. Take out your cell phone and text your mom or your dad, whoever would be better at this, and say, I need a can for math tomorrow. Because you know you're not going to remember it, but if you text them, there's a chance that between the two of you, one of you will remember it tomorrow. Go ahead, do it. I need a can. It can be like a soup can or whatever. And I would love it if there's a diversity of cans. Like some people had tall, skinny ones. Some people had short, fat ones. Some people had kind of normalish ones. Okay, so if you find unusual shaped cans, they have to be a cylinder. They can't be like a cone. They have to be just a straight-sided can. Pop cans would not be good. It needs to be more like a soup size. Doesn't have to be soup. It could be a lot of different things that come in a can. Peaches, whatever. Canned corn. It's had all different kinds of cans. Yes? Good question. No, don't empty it. Bring it full. Because if you want, at the end of this, I will donate it to the food shelf. And it's Thanksgiving time. It's a good time for that kind of thing. That way you don't have to carry it back home again. And it's a donation to those less fortunate. I'm going to pause for a second and talk about that for a minute. So enough about the can lab for now. And let's look at the hot dog eating contest. So this is a rate. Now people actually do this. I'm going to show you a little video clip. I'm going to stop. If you want to go look, just Google hot dog eating contest on the search bar in YouTube, and you'd find these. I'll pause while we play that. So a little bit of canceling here. I kind of like using 8 times 10. I don't know if you remember me saying that, so that I can make the 10s cancel. And instead of using 80, I would use 8 times 10, which in this case didn't really help me much. 8 times 10 is 80x. So now I've got 70 times 8 plus 80x is equal to 8 times 10. Here it helps again. And that's 10 times 100 is 1,000. And then I need to take 8 times 7 is 56, add a 0, 560. Now I'm going to subtract 560 from both sides. And you have 80x equals 440. Is that right? Okay. And then I have to divide by 80. And then I can reduce this thing. Zeros can cancel. 44 divided by 8. Anybody tell me what 44 divided by 8 is? X equals 5.5. Very good. What do we just figure out? There's 5.5 chickens in Rwanda? No. But there's 5.5 what? Hot dogs per minute. That's this guy's rate. Does that actually answer my question? No. My question was, how long will it take him to eat 30 hot dogs? So then I need to know that rate times time gives you your distance, or in this case, dogs. The rate, 5.5, times the time, which I don't know. So I take x, will equal 30. And now x must equal 30 over 5.5. Now that you can use a calculator for, and the calcs are going to be allowed in this next test, so once you grab your graphing calculator, take it out, you're going to be able to use calcs. So I know we could have solved it that other way, but grab a calc, and what is 30 divided by 5.5? I think it's close to 5.5 again. 5 point something. Isn't it 5.4 something? Okay, 5.45. Now that is an important distinction because this gets confusing. 5.5 was his rate, but the time is 5.45, and that's different. 5.45 what's? Minutes. So it will take him about 5.5 minutes to eat 30 hot dogs. All right. Now, let me show you how we could have set this problem up smarter. Instead of figuring out his rate, do you get, we could have said, we want to know how long it'll take him to eat 30 hot dogs. So 30 hot dogs would be done in X amount of time. And then we'd figure out X, and guess what? Look, it's exactly the same as this. I would have figured out that X, his rate, would have been 5.5. And then how long it actually takes him? 5.45. So this would have come out to 5.45, which is the exact answer to the question that we had. We already got 5.45, but we did it a longer way. Do you see how it could have been smarter to set it up this way? All right, I'm going to give you another one. And if you feel a little confused right now, that's normal. I went and talked to one of my teachers that I go to who has taught this class for 9 years. And they took out their notes to explain it to me. Even after having taught it for 9 years. Because it can be confusing and you can set them up wrong by accident. Okay, so don't be surprised if these cause you a little consternation at first. But after we do a few, I think you'll like them. They aren't that bad. All right, the next problem has to do with Mr. Server and weed. So I used to have to pick weeds for my dad. They were just, oh, you thought something else? We were just growing like dandelions and things like that. None of those other weeds, which wouldn't be legal in Minnesota anyways, although in some places it is. So if I went in the backyard and picked weeds, basically I had to, just because I lived in the house and I had to do my part to help out, I still am a little bitter about it. I can still picture that backyard and looking at it going, there's so many weeds. What do you really want me to pick all the weeds? That's insane. There's so many of them. But that was part of growing up and helping out. So I would pick for maybe an hour. And let's take it down to the minute and take my hourly rate and come down to, let's say I was not terribly motivated. Let's say that in 1 minute, I was able to get 5 weeds. Now, I know some of you are just thinking, can't you just rip weeds out of the ground a lot faster than that? Well, maybe I was trying to get the roots, because that's what my dad really was focusing on. If you just take the top off, it's just going to grow back again. Got to get them by the roots. So 5 weeds in 1 minute. Let's say the kid down the block, I'm going to pause for a second. Okay, So let's say the kid down the block gets hired to do this job, and his rate's going to be added in with mine, but I don't know how fast he picks. So what am I put there? I could put an X there and figure out this kid's rate. But I know that together, in 25 minutes, we had a pile of 400 weeds. Now, if I was asking you how fast was the neighbor kid, you just have to solve for X. I don't have the X up there yet, but there it is. Notice rate plus a rate equals a total rate. Do you get how you'd solve this by multiplying by 25 everywhere? See, from there it wouldn't be too hard, right? Could you get, I could graph both sides and see where they cross. I could graph that and that, y equals both sides, and see where they cross. It would work. Okay? And then I get a rate. Now, let me ask you this. What if I had said, how many weeds can he pick in 12 minutes? Do you get, I could have put it as that then? Yes. Absolutely. So that's part of solving this thing. So that's, yep. So you reduce this to what? Oh, nice. 400 divides by 25 nicely. Do you get if that had been a 26, that wouldn't work. But you're right that you could do any reducing anywhere you can. So, all right. Did somebody actually solve this yet? 5 plus x equals 400 over 25. I want to multiply by 25 in all three parts. But actually, how about if I do it smarter than that? She just told me that equals 16. They make it a lot easier. And then what's x got to be? So he picks 11 weeds per minute. Obviously more motivated than me. Maybe he's paid by the weed. My dad did that for leeches. That was a very effective method. Go into the, there was the lake that we were on up north had this inexplicable, like, huge population of leeches. And my family single-handedly destroyed the ecosystem up there by picking all the leeches out of there because he offered 10 cents a leech. And they were all over the place. So instead of being like, ew, it's a leech, we were like, ooh, 10 cents. Grab it, put it in the bag, show the bounty, and it works. Back in the old days, they used to do that for coyotes in South Dakota. People would, there was just coyotes like everywhere. And so they were eating the farm animals, they were eating people's dogs and cats. It even happens today. Like my neighbor has lost 2 cats to coyotes. So anyway, there were so many coyotes back then that they put a bounty on coyotes. So anyway, this kid was really motivated. He got 11 weeds per minute where I was only getting 5 weeds per minute. Okay, so that's a typical example. Notice the theme. A rate plus another rate equaling the total rate. Does that make sense? All right. Now, I have one more thing to teach you. But before I move on, we're far enough. I have to get to the last thing. All right. So this is your assignment. Now everybody get to this page. And I'm having you do all of them on this page, except I talked a little too much in your hour, so we're going to skip one problem here. We're going to skip this one. The only catch on this one is you would not have been able to find asymptotes for it because you can't crash the thing. So you get why you can't crash it? You can't find something to make the denominator part ever be 0 because x squared would have to equal -1, and it can't. So anyway, crossing that off. Number 1, how are you going to solve this? It's just a complicated denominator, so whenever you get denominators, you multiply by the denominator. So I'm going to multiply by 5x plus 4 on both sides. And that cancels that. x equals 3 times 5x, 15x. 3 times 4 is 12. If you can't solve that, I'm scared for you. You're just going to have to do a little simple algebra and you get the answer. Okay, subtract x from both sides, subtract 12, etc. All right, same thing with number 4. You just have a denominator, get rid of it. But I want to warn you, there's extraneous things. The answer to this may come out to like x equals -1. Let's say it did. What's wrong with that? Yes, sir. It crashes the function. So it's an answer that's not really an answer. I had a friend, actually wasn't a friend, he was just a guy I met playing cards, and he had a finger that wasn't a finger. It was an extraneous finger. Have you ever heard of having 6 fingers on a hand? It's rare, but it's like one every, I don't know what it is, I think it's like one every 10,000 births. It's not super rare. I mean, it happens like often at hospitals, like probably, you know, every couple of weeks or whatever. Big hospital maybe. They're going to have a baby that's born with an extra finger. Do you know what they do with it? They lop it off. That's right. They do not want to keep an extra finger around, especially because they pretty much never work. Now, there's a James Bond movie about a guy who had the 6th finger. Ever heard of that? I think it was Goldfinger. Anyway. And if you had 6 fingers that were functional on your hand, that'd be an interesting question. If you had a little baby that just got born with 6 fingers, but they all worked, would you let him keep the finger? And if you did, you get how you might get teased mercilessly? You never find gloves? But I think I might keep it too. Give him mittens. I like that answer. Okay, good. So anyway, the extraneous finger, he would play with it playing cards like, you know, you can like do this to your finger. It worked really good with that extraneous finger hanging there. And he would just go like, boing, 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 boing. And it would just like bobble all over the place on his hand. It didn't work at all, but man, it was distracting. I still remember it vividly to this day because it was extremely distracting. Well, that's an extraneous finger. It's a finger that doesn't really work. This is a solution that doesn't really work because, why? Because it would crash. If you actually put it in, it would actually crash your function. So you have to watch out for this, and you have to watch out for square roots. If you have a square root that's like this, and you come up with an answer of, it's a really complicated question, but you get an answer of x equals -5, do you get when you actually put it in? It won't. Well, actually, that wouldn't be a problem. -6, there we go. That actually won't work. It's not legal. Has a square root of a negative. Okay, so you got to watch out for square roots, and you got to watch out for fractions like this. And when you plug the answers back in, you need to check them. Did I just say you have to check every single answer in your test? No. I said you had to check every single answer where there was a fraction or a square root, because those are the times when your answers might not actually work. So especially when the directions say, be sure to check for extraneous solutions, you can figure that's going to happen. All right, and that page is really easy. This next page is also easy, but it's different. Let me show you. See how it says greater than? It changes everything. You can no longer multiply by x plus 2 on both sides, which is what you would have thought. Because if you multiply by a negative on both sides, you'd have to switch that sign. But if you're multiplying by a variable, you don't know if you multiplied by a negative? That's my way of explaining it. But you can't multiply by x plus 2 on both sides here. You're not allowed to multiply by a variable when there's an inequality. So what do you do instead? You find the zeros and the roots. And do you get -2 is important here? That can't be -2. And then the only question is, it could be bigger than that or it could be less than that. Let me think. If I put in 0, that's bigger than that. I'm going to put 0 into the function. See how quick this is? It's just 1 over 2 is greater than 0. 1/2 is bigger than 0. It works here. And you stick in something smaller than -2, like -3. 1 over -1 is -1. Is -1 bigger than 0? No, it's not. Cross it off. So you have to test intervals. You've been testing intervals now this is the 3rd chapter where you've tested intervals. So it shouldn't be super hard for you. Let's just start number 8 together. But there's two things. -2 is one of them. What's the other thing that I got to put on my number line? 3. Because even though it doesn't crash the function, it's a 0. So it's an important spot. I need to extend my number line a little bit here. Because now I got to test 3 intervals. I got to test something in here, something in there, and something in here. And I'll just test one of them for you. Let's say I test something bigger than 3, like 4. I get 1/6 is 1/6 less than 0. No, it's not. 1/6 is not less than 0. And therefore, that didn't work. So it doesn't work there. I bet it works in between. Let's test. So what's in between these? 0's in between them. So I get -3/2, which is a negative number. Is a negative number less than 0? Yes, it is. It works in there. And it probably doesn't work out here, but sometimes they do. You best test all 3 zones. All right, I have done a significant part of that page. And then the last page here are these rates. I want you to skip number 22, and I want you to skip number 24. But you should do the llama question. It's nice, straightforward. Rate plus a rate equals a rate, just like we did in class with the weed picking and the other one, the hot dog eating. Okay. And this one, number 21, might be the only one that'll be a little bit of a challenge for you. But again, you're skipping 22 and 24. A little longer tonight. I do want to warn you that tonight's homework, tonight's won't be that bad. Tonight's won't be bad at all, but tomorrow's is harder than normal. There's going to be every now and then, as you know, in classes, harder lessons. It's word problems, and you will struggle with them a little bit to figure out, how do I set this up? But trust me, if it's in the section about, life's a lot easier than it is in the real world, because we're in a section about fraction problems. Do you get there's probably fractions involved in these? You just figure out what the fractions are. It's usually just adding a couple fractions when it's all said and done. But they can trick you. Like I said, people have to take out their notes sometimes when they're in this section. Okay, that's all I got for you for today. Okay.